All right, so we've talked about how alkyl halides can do those substitution reactions, which is really important. But I want to address how those alkyl halides can do something else that's really interesting. Well, you'll notice that in those alkyl halide reactions, we used a nucleophile. Our example was water, but there could be lots of different nucleophiles. There's a ton of options, and it really affects things. But I want to tell you something that we have to bear in mind for the rest of organic chemistry, and this is something you're already pretty familiar with. A nucleophile, we remember, is really just a Lewis base, right? It's giving its electrons to something that's a Lewis acid. Well, you're going to want to remember also that a nucleophile is very similar to a base or can be a base. Like water, for example, that we used in our last example. Water is a nucleophile, but water is also a base. Of course, we know that water is a base. We've been doing that for years in chemistry. So I'm going to tell you that we can also have something acting as a base. Well, let's take a look at a really interesting effect that has. Let's say that we have some alkyl halide, and here is our alkyl halide. And that alkyl halide has two H's, but it also has this carbon over here, and this carbon has 3 hydrogens on it. Well, if this base was to go and grab a hydrogen here, would that be possible? Well, normally we'd say no, of course, because that hydrogen is held really strongly to a carbon. A carbon-hydrogen bond isn't going to break. I mean, the pKa is like 50 for that thing to work as an acid. And normally that would be true. But you have to remember that there's a very, very weak bond that wants to break heterolytically over here. And as that bond breaks heterolytically, as the electrons are pulled towards that bromine, it's going to leave behind what is essentially an empty p orbital. Well, if we had another p orbital here, what could we do with that? Well, we've just spent several chapters learning about alkenes, right, which is a bond between two p orbitals. So you're probably already seeing the direction we're going with this. As this bond is able to break and the base is able to grab that hydrogen, we have these electrons right here that need to go somewhere. And there's a very stable place that we can drive those to. Those electrons can immediately go right here into that pi orbital. We call this type of reaction, or this step, as you've already seen this, by the way, in the aromatic chapter. At the very end, we already introduced this, but this is called and I'll put it in red here, an elimination reaction. So elimination reactions are really common with alkyl halides because we have that halogen that's weakening the bond, and we can always grab a proton on the carbon one away and form this alkene. So again, this is an elimination. But you're probably already seeing our problem here. You're saying, hold on, couldn't this nucleophile also attack the carbon and then that Br leaves? And wouldn't that lead to a substitution product rather than an elimination, right? So here's our substitution product. You're right, it would. So we have a constant competition in this entire chapter, and really all of organic chemistry, between these options. And you'll notice there is a fundamental difference between them. Whatever we use as our nucleophile is either going to be a nucleophile or it's going to be a base. And these are the factors that end up contributing to whether it's going to be a substitution or elimination. There are a lot of other factors that are going to help us control whether it's a substitution or elimination. And that is something that we want to give some time to and talk about. But the fundamental difference is whether our attacking group is going to act as a base. Remember, a base is literally defined as picking up a proton. Or if it's going to act as a Lewis base, or nucleophile, where it's donating its electrons and forming a new bond with this compound, right? So to show you overall, of course, what this would look like if you looked at an elimination, I'll give you an example. So let's say that we have some alkyl halide again here, and that alkyl halide has a Br here. What would happen if we put in a nucleophile, or a base, and in this case for the base, I'm going to use a nice strong base. I'm going to say we'll do sodium ethoxide. So this sodium is positive and the oxide is negative. What we're going to have, let's say, is that sodium ethoxide is going to come over here and grab this proton. These electrons are going to move right here, forming that alkene. But of course, at the same time, we're also going to have this Br coming off because that's the only way we can form that new bond. So what are our products going to be of this reaction? We're going to get this ethene right here, our protonated alcohol, right? Because this ethoxide has now grabbed that proton. Our other product is going to be our sodium bromide, which is just a simple salt. So these are our three products of this reaction. Now let me differentiate that in a really important way for you. If this ethoxide was to go and backside attack this carbon and the Br were to come off, what would we get instead? So this would be our substitution, right? This is our elimination product. And actually, let me put that in the proper color for you with that purple arrow. So we're just going to say elimination. Let me draw the substitution product for you right here, and I'll put that in green because that's our green arrow. CH3 hanging out here still. We're going to have CH2. We're going to have our O attached here. So this is, as you can see, making an ether. But notice there is also one other product we're going to get. We knocked our Br off, right? So we're also going to have Na+, and we're going to have our Br negative. So there's a fundamental difference here that's really important that I want you to bear in mind. We have two products of substitution, just like we had two reactants. But in elimination, we went from 2 to 1, 2, 3 separate things. Now, why is this important? Well, this is really important because we remember delta G equals delta H minus T delta S. And if you recall, you remember that delta S is entropy. What happens if we go from 2 things to 3 things? What's that going to do for us? It's going to be a nice increase in entropy. Now, what we notice is that there is our heat here, our temperature. If we have more heat, that increases the favorability of this term. This is one of the reasons why, if we heat our product, we can drive it more to elimination because we're forming more products. Okay? Give you one other little tip, and then we'll go through these in detail more in future. But my other small tip for us here is that if we look at our base or our nucleophile, the ability to grab an H is much easier than the ability to sneak in here between all of the big bulky Br and this carbon and all that, and to grab that carbon. The steric hindrance is affecting us. So what would happen if we start to put more things onto the alkoxide? Well, it's going to make it much less likely to be a substitution, and it's going to be much easier for it to do this elimination. So that is one more example of how we can push things towards substitution and elimination. The bulkiness of our attacking group and heat are two really important ways we can do that. When we look at elimination, we have two types of elimination. Just like we had substitution of SN1 and SN2, with elimination, we have E1 and E2. What does that mean? Just second and first order elimination. Well, how would we have a first order elimination? Pause it and think about what it would be. By the way, hint, it would be dependent on the type of alkyl halide. That's how we're going to choose between these. think about what it would need. All right, I'll tell you what it would need to choose between E1 and E2. It's the same as what you need to choose between SN1 and SN2. If you have a very substituted alkyl halide, then of course it's going to be able to leave, and now you're going to have a carbocation here. That carbocation also has hydrogens, so of course the base, you should draw this reaction mechanism out for yourself in completion, but this shows us that we can take a base, grab the proton, and we already have a carbocation here, so it's very easy to eliminate and form that alkene, right? So we're going to form an alkene here quite easily. Whereas an E2 reaction, we would have a much less substituted, so it would take a base, grabbing the proton and forcing this Br away, just like the SN2 reaction, where we're going to have both the base and the alkyl halide in the rate law, right? We're going to have both the base and the alkyl halide in our rate law in this E2 reaction, just like our SN2 reaction. So, but of course it's going to be grabbing a proton because it's a base, not a nucleophile in this case, giving us an alkene. So that's how we can select between E1 and E2. It's the same as SN1 and SN2. Now, how to select between these different options, substitution and elimination, I gave you 2 hints, but we'll talk about more details, how solvent affects this, and all of these things affect it in future.